Imagine for a moment that you are floating in absolute darkness. Not the darkness of a room with the lights off, not the darkness of a forest at midnight, but a darkness so complete, so total, so ancient, that light has not touched it in perhaps a billion years. Above you, pressing down with a weight that would crush any submarine ever built by human hands, stretches a ceiling of ice 4 miles thick. Below you, the ocean floor glows with the dim heat of hydrothermal vents, and the water around you is warm and mineral-rich and chemical and alive with possibility. You are not on Earth. You are beneath the frozen surface of Europa, one of Jupiter's moons, and you are wondering, as every scientist and dreamer who has ever pointed a telescope at this small, cracked, brilliant world has wondered, is something else here with you? This is not a story about science fiction. This is not a thought experiment pulled from the pages of a novel. This is the story of one of the most extraordinary places in the known universe, a moon that orbits a gas giant 390 million miles from the Sun, a world smaller than Earth's own moon, and yet a world that may contain more liquid water than every ocean, every lake, every river, every raindrop, and every tear ever shed on the surface of our entire planet combined. This is the story of Europa, and the 22 mysteries that surround its hidden ocean. Mysteries so deep, so strange, and so potentially world-altering that even the most careful, most conservative, most peer-reviewed scientists in the world have begun to whisper words they would never have dared whisper a generation ago. Words like life, words like intelligence, words like something we have never imagined before. Let's begin at the beginning, because to understand what makes Europa extraordinary, you first have to understand why it exists at all, and why it should not, by any reasonable measure of celestial physics, be the way it is. Jupiter is a monster of a planet. It is so large that all the other planets in our solar system could fit inside it with room to spare. It generates a magnetic field so powerful that it would be visible from Earth as a structure larger than our own moon, if only our eyes could see magnetic fields. And it is surrounded by dozens of moons, some large, some small, some volcanic, some icy, each one a world unto itself. Europa is the 4th largest of Jupiter's moons, roughly the size of Earth's own moon, and from a distance, it looks almost unremarkable, a smooth, pale sphere of ice, reflecting sunlight like a billiard ball wrapped in cracked glass. But that crack is the key. The entire surface of Europa is covered in reddish-brown lines, crisscrossing in every direction, stretching for thousands of miles, overlapping each other in patterns so complex and so chaotic that they look from orbit like the veins on the back of a hand, or the fractures in the shell of a hard-boiled egg, or, if you let your mind wander into the territory where science meets imagination, like the highways and roads of some vast, ancient civilization that existed before humanity was even a spark in the universe's eye. These lines are called linei, a Latin word, because scientists often reach for Latin when they want to give a name to something they don't yet fully understand, and they are among the first and most enduring mysteries of this world. What made them? What continues to make them? And why, when you compare images taken decades apart, do they keep changing? Here is something that will stop you in your tracks. The linei on Europa's surface are not cracks in static ice. They are evidence of a living, breathing, dynamic system beneath the surface, a system driven by one of the most powerful forces in our solar system. Every 3.5 Earth days, Europa completes one full orbit around Jupiter. During that orbit, the gravitational pull of Jupiter stretches and squeezes Europa like a rubber ball being rolled between giant hands. This process, called tidal heating, is the same force that makes the inside of a marshmallow warm when you squeeze it back and forth in your hands, except that in Europa's case, the force is so immense and has been operating for so long that it has kept a liquid ocean beneath the ice for what scientists believe may be billions of years. Without Jupiter's gravity, Europa would be a frozen rock. With it, Europa becomes something remarkable, a world with a persistent, global, potentially habitable liquid water ocean, sitting in the outer solar system where sunlight is barely stronger than starlight, and where the temperature on the surface plunges to minus 160 degrees Celsius. Ask yourself this question right now. What does it mean for a place to be habitable? Most of us, when we think about habitable, think about something like Earth. breathable air, liquid water, moderate temperatures, a yellow sun in the sky. But life, as we have increasingly discovered on our own planet, does not share our preferences. Life exists in boiling acid hot springs in Yellowstone. Life exists in the crushing dark of deep ocean trenches 3 miles beneath the surface of the Pacific. Life exists in the frozen dry valleys of Antarctica, in solid rock, in radioactive waste, in the vacuum-adjacent edges of our atmosphere. Life is not delicate. Life is not particular. Life, it turns out, is extraordinarily stubborn, and the places where we assumed nothing could possibly survive have turned out, again and again, to be places where life thrives, innovates, and evolves strategies we never could have predicted. Europa has liquid water. Europa has chemical energy, delivered by the tidal forces of Jupiter, converting mechanical squeezing into heat and chemical reactions. Europa almost certainly has a rocky seafloor, which means it almost certainly has hydrothermal vents, cracks in the ocean floor through which superheated, mineral-rich water flows upward into the cold ocean above. And those hydrothermal vents, here on Earth, are home to some of the most bizarre, most beautiful, and most resilient ecosystems on the planet. Tube worms that grow longer than a human being. Eyeless shrimp that navigate by heat rather than light. Bacteria that consume hydrogen sulfide and breathe sulfur. Entire food chains built not on sunlight but on chemistry. If this can happen here, then ask yourself, why not there? But here is where the mysteries begin in earnest, because Europa does not just offer the possibility of life. Europa offers something stranger, something more complex, something that has kept scientists up at night for decades, not because they are afraid, but because they genuinely do not know the answer. And science, real science, is defined by the questions it cannot yet answer. The first mystery of Europa is deceptively simple, and it is this: where did all the water come from? Europa is estimated to have a liquid ocean containing somewhere between 2 and 3 times the total volume of water found in all of Earth's oceans combined. Think about that for a moment. Stand on the beach, look out at the Atlantic or the Pacific, feel the scale of it. The horizon so far away it curves with the shape of the planet, the depth beneath you that plunges for miles, and then multiply that entire experience by 3, and then do it again for every ocean on Earth, and then triple the result. That is how much water Europa may contain. And the question of where this water came from, of how a moon that formed in the outer solar system accumulated that much liquid water, is one that planetary scientists are still actively debating. The leading theory involves ice-rich material from the early solar system, combined with the heat generated by Jupiter's tidal forces, combining over billions of years to melt and sustain a global ocean. But the details of exactly how, and exactly when, and exactly what conditions allowed this to happen remain deeply uncertain. The second mystery is one that nobody talks about as much as they should, and it might actually be the most unsettling of all. It is this: Europa's surface is young. Not young by human standards, but young by planetary standards. The surface of our own moon is covered in craters, billions of years of impacts recorded in stone, each one a scar from a different collision with a rock from space. Europa, in contrast, has almost no craters. The few that exist are small, and some appear to have been partially erased, filled in, or distorted. This tells us something extraordinary. The surface of Europa is being constantly renewed. Material from below is coming up. The ice is moving, flowing, fracturing, and reforming. This is geologically active ice, and it is one of the clearest pieces of evidence we have that the ocean beneath is real and ongoing. But it also raises a deeply uncomfortable question. If the surface is being renewed from below, what is doing the renewing? What is pushing up through the ice? And what, if anything, is coming with it? The third mystery is the color. Europa's surface is not uniform white. It has regions of deep red-brown, almost rust-colored material concentrated particularly along the lineae, the great crack systems that crisscross the moon. This material has been analyzed from afar using spectroscopy, which is the science of reading what things are made of by looking at the light they reflect, and the results have been, to put it gently, wildly suggestive. The reddish-brown material appears to contain complex organic compounds and salts that may have been delivered to the surface from the ocean below. Some scientists have proposed that it could be sulfur compounds. Others have suggested it might be related to magnesium sulfate, Epsom salt, essentially the kind you put in a bath. But a small and growing number of researchers have raised the possibility that some of the organic compounds in those reddish streaks are the kinds of compounds that, on Earth, are associated with biology. Not proof of life, not even strong evidence of life, but the kind of chemical fingerprint that makes you stop and look twice, and then look a third time, and then reach for the phone to call a colleague. Ask yourself this: if you found a red-brown stain on a surface and someone told you it might be salt, or it might be something biological, how would you feel? Now imagine that surface is 1 billion miles away, and you can't go and scrape it with a fingernail to check. That is the situation every scientist working on Europa lives in every day. The fourth mystery is one that has taken on enormous importance in recent years, and it is the question of Europa's plumes. In 2013, astronomers using the Hubble Space Telescope spotted what appeared to be water vapor erupting from near the south pole of Europa. Enormous geysers or plumes shooting up hundreds of kilometers above the surface. This was electrifying news, because if Europa is venting water from its ocean directly into space, then we don't need to drill through 4 miles of ice to sample that ocean. We could potentially fly a spacecraft through those plumes and collect samples directly from the ocean itself, analyzing them for chemistry, for organic compounds, for biosignatures. The scientific community erupted, pun fully intended, with excitement. But then came the problem. Follow-up observations did not always confirm the plumes. Some observations showed them. Some did not. The signals were inconsistent, intermittent, frustrating. Were the plumes real? Were they a measurement artifact? Were they there sometimes and not others? As of the time of this writing, the scientific consensus is that the plumes are probably real, probably intermittent, and probably an extraordinary opportunity, but probably is doing a lot of heavy lifting in that sentence. The fifth mystery takes us deeper, literally and figuratively, into the structure of the ocean itself. We know Europa has an ocean. We know it is liquid. But we do not know how deep it is, how warm it is, what its chemistry is like at different depths, or whether the ocean is uniform or divided into distinct layers with radically different conditions. On Earth, the deep ocean is not one homogeneous environment. It has thermoclines, haloclines, pressure gradients, oxygen minimum zones, and a whole variety of ecological niches created by changing physical conditions. Europa's ocean could be equally complex, or it could be far more complex, because it is sealed off from sunlight entirely and driven by a fundamentally different energy source. The current best estimates suggest the ocean is somewhere between 60 and 150 kilometers deep, roughly 100 times the average depth of Earth's oceans. But this comes with significant uncertainty. And the question of what lies at the very bottom of Europa's ocean, where the water meets the rocky mantle, is one of the most tantalizing unknowns in all of planetary science. Here is where things get very interesting. On Earth, the deepest point in any ocean is the Challenger Deep in the Mariana Trench, about 11 kilometers below the surface. Europa's ocean may be more than 10 times that deep. And at the bottom of that ocean, where the pressure is unimaginable and the darkness is absolute, the rock of Europa's mantle is being continuously kneaded and heated by tidal forces. This means chemical reactions are happening constantly between the rock and the water. Minerals are dissolving. Compounds are forming. Energy is being released in the form of heat and chemical gradients. The ocean floor of Europa may be one of the most chemically active environments in the solar system, a perpetual chemical laboratory that has been running, without interruption, for billions of years. The sixth mystery is the one that keeps astrobiologists lying awake at night staring at the ceiling, and it is the question of time. Life on Earth took hundreds of millions of years to emerge after the conditions became right, or at least that is one interpretation of the fossil record. But the conditions on Europa have been relatively stable for billions of years. If the ocean has been liquid for even a fraction of that time, say, 1 billion years, then we're talking about an environment where life would have had more time to emerge, evolve, and potentially develop complexity than early Earth had available. If chemistry can become biology given enough time and the right conditions, then Europa, with its ancient, persistent, chemically active ocean, may be one of the best bets in the solar system. The question is not whether the conditions are right. The question is whether we are confident enough in our understanding of how life begins to make predictions about a world we have never visited up close. And this brings us to a question worth sitting with for a moment. We have exactly one example of life in the universe, the life on Earth. Every theory about how life begins, every model of what conditions life requires, every prediction about where life might exist, is based on a single data point. One planet, one origin event, one lineage of life that has diversified into millions of species over billions of years, but all descended from a single ancestral chemistry. When you make a prediction based on one data point, you are not doing statistics. You are guessing. An educated guess, a deeply informed guess, a guess shaped by decades of brilliant science, but a guess nonetheless. Europa could vindicate that guess completely. Or Europa could reveal that life requires something we have never thought of, something not present there despite the water and the chemistry and the energy. Or Europa could reveal something so utterly alien to our expectations that it forces us to completely rewrite our understanding of what life is. All three of these outcomes would be transformative. All three of these outcomes would change everything. The seventh mystery is one that has become famous in popular culture, partly because it is so vivid, and partly because it forces you to contemplate a possibility that is equal parts thrilling and disorienting. It is the question of what, if anything, lives in Europa's ocean, and specifically whether that life could be large, complex, macroscopic, visible, the kind of thing that swims. Here on Earth, complex multicellular life, animals, in other words, emerged about 540 million years ago in an event called the Cambrian explosion. Before that, for roughly 3 billion years, life on Earth was almost entirely microbial. The Cambrian explosion seems to have been triggered, at least in part, by rising oxygen levels in the atmosphere, which provided a new and highly efficient energy source for complex metabolic processes. Europa, lacking photosynthesis and therefore lacking the oxygen-generating engine that transformed Earth's biosphere, might be stuck at the microbial stage indefinitely. But here is the thing. Photosynthesis is not the only way to generate chemical energy gradients that could power complex life. Tidal forces, hydrothermal venting, and chemical gradients between different layers of the ocean could theoretically provide energy pathways for increasing biological complexity, even without sunlight. And some researchers, speaking carefully, speaking theoretically, speaking with the appropriate hedges and qualifications that serious science requires, have not ruled out the possibility that Europa's ocean could contain not just microbes, but something more. And this is where the phrase space whales enters the conversation. It is not a scientific term. It does not appear in peer-reviewed papers, but it has become a kind of shorthand for a deeply serious question. Could an isolated, ancient, mineral-rich, tidal energy-driven global ocean, sealed beneath miles of ice and running for billions of years, produce animal-like life? Creatures that swim, creatures that hunt, creatures that have nervous systems, or something functionally analogous to nervous systems. When scientists like Brittany Schmidt at Cornell University talk about the possibility of a layered, complex ocean with different ecological zones, when they describe the potential for chemical energy to drive not just microbial but perhaps larger biological processes, they are not talking about science fiction. They are asking a real question, and the honest answer to that real question is, we don't know. And in science, we don't know is not a failure. It is an invitation. Think about it this way. If you had told someone in 1850 that the deepest parts of Earth's oceans were home to 6-foot tube worms and shrimp that see through heat, they would have laughed you out of the room. If you told them that bacteria survive in solid rock a mile underground, they would have suggested you see a doctor. Our own planet has surprised us, repeatedly, profoundly, and with increasing regularity as our instruments improve and our willingness to look in strange places grows. So when we approach Europa, we should bring with us not just our best instruments and our most rigorous science, but also a deep and genuine humility about what we think we know. Because the universe has a long history of making fools of the overconfident. The eighth mystery is the ice itself. Specifically, how thick is it, and does it connect to the ocean? This might sound like a question with a straightforward answer, but it is, in fact, one of the most contested and consequential debates in Europa science. Early models suggested the ice shell might be just a few kilometers thick, thin enough that material from the ocean below could relatively easily reach the surface, creating the geological activity and chemical mixing we observe. More recent models, incorporating data from the Galileo spacecraft that orbited Jupiter in the 1990s and 2000s, suggest the ice may be significantly thicker, perhaps 20 to 30 kilometers in some places. This has profound implications for the possibility of life in the ocean, because if the ice is thick, it acts as a barrier not just to our instruments, but potentially to chemical exchange between the surface and the ocean. The surface of Europa is constantly bombarded by radiation from Jupiter's magnetic field, which breaks water molecules apart and creates oxidants, hydrogen peroxide, molecular oxygen, and other compounds. On Earth, oxygen is the great energizer of complex life. If those surface oxidants can make their way through the ice into the ocean below, they could potentially supercharge the chemical energy available to any life in the ocean. But if the ice is thick, this transfer may be slow, limited, or blocked entirely. The thickness of Europa's ice is not just a geological question. It is potentially a question about whether Europa's ocean is energetically rich enough to support complex life. The ninth mystery brings us to the surface features that have no clear explanation, and the one that haunts me most is called chaos terrain. Europa's surface is divided into two broad categories: the older, smoother plains of older ice, and chaotic regions where the surface appears to have broken apart, shifted, refrozen, and resolved itself into a jumbled landscape of tilted ice blocks, dark matrix material, and disrupted geology that looks, at the resolution of our best images, like a pack of ice that has been stirred by some gigantic invisible spoon. On Earth, we see something similar in the Arctic when sea ice breaks up in summer and refreezes in winter. But on Europa, the scale is planetary. Entire regions the size of continents have been churned and disrupted, and the mechanism that drove this disruption is thought to be the upwelling of warmer ice or even liquid water from below the surface. The chaos terrain may be evidence of places where Europa's ocean came close to, or perhaps actually reached, the surface. And if that is true, those regions may be windows into the chemistry of the ocean below, preserved in the refrozen ice of the chaotic landscape like a message in amber. Scientists have proposed sending landers specifically to chaos terrain regions, because the material there may contain the best evidence of what exists in the ocean below, without requiring us to drill through miles of solid ice to get it. Let me pause here and ask you something. If you had the chance to read a message from an alien ocean, not a message in language, not a code or a signal, but a chemical message written in the composition of ancient, refrozen ice, would you be able to decode it? Would you even recognize it as a message? This is exactly the challenge that awaits the scientists who will analyze the data from Europa's surface. Chemistry can tell stories. Molecules can carry the echoes of the processes that created them. And if life has ever existed in Europa's ocean, it may have left its molecular fingerprints in the ice above, waiting for someone with the right instruments to come along and read them. The 10th mystery is about radiation, and it is one of the most sobering facts about Europa. Jupiter's magnetic field is enormous and powerful, and it traps charged particles, electrons and ions, in vast radiation belts that surround the planet. Europa orbits within these belts, and the radiation environment at Europa's surface is brutal. A human being standing unshielded on Europa's surface would receive a lethal dose of radiation in a matter of hours. The radiation breaks down organic molecules, sterilizes the top layers of ice, and creates a relentless chemical assault on anything at the surface. This is actually why some scientists think the plumes are so exciting. They offer a way to sample the ocean without having to deal with the radiation-processed surface material. But it also raises a fascinating and counterintuitive question. Could the radiation itself be, paradoxically, a source of energy for life in the ocean? The oxidants created by radiation breaking down water molecules at the surface may percolate down through the ice over geological timescales and into the ocean, where they could serve as the oxidizing agents that power metabolic reactions. So the radiation that makes the surface deadly may, indirectly, be making the ocean livelier. This is the kind of elegant, counterintuitive twist that the universe seems to specialize in. Here is a question to consider. When we talk about what makes a planet or moon habitable, we usually think about threats to life. Too hot, too cold, too much radiation, too little chemistry. But what if some of those threats are also, from a different angle, the very forces that make life possible? What if the deadliness of Europa's surface is not an obstacle to life in its ocean, but one of the engines driving its chemistry? The 11th mystery is about Europa's relationship with time, and specifically about the timeline of its geological history. Europa's surface, as we noted earlier, is young, perhaps only 20 to 180 million years old, based on crater counts. This means the surface has been completely renewed within a time frame that, on geological scales, is quite recent. But this renewal is not uniform. Some regions are older than others. Some lineae cut across older lineae, suggesting multiple episodes of activity over time. What is driving these episodes? Is Europa's tidal heating steady and continuous, or does it wax and wane? Some models suggest that Europa may go through cycles of more intense and less intense tidal heating, driven by resonance interactions with the other Galilean moons, Io, Ganymede, and Callisto, which are all locked in a gravitational dance called the Laplace resonance. If Europa's geological activity is cyclical, then the ocean may have periods of greater chemical activity and periods of lesser activity, and life in the ocean, if it exists, may have evolved not in a stable, steady environment, but in a pulsating, rhythmically changing one. Life that has evolved in cycles of feast and famine, activity and quiescence, may have developed strategies we have never imagined, because on Earth, we have nothing quite analogous to a global ocean sealed beneath miles of ice and driven by the gravitational heartbeat of a planet 12 times Jupiter's diameter. The 12th mystery is perhaps the most technically demanding, and it is the question of how we will ever actually prove whether life exists in Europa's ocean. This is not a trivial problem. Even if we land a spacecraft on Europa's surface, we still face the challenge of the ice. Drilling through ice that may be 20 kilometers thick, with autonomous robotic systems, in a radiation environment that would destroy most electronics relatively quickly, in a gravity well defined by Jupiter's enormous field, at a distance of hundreds of millions of miles from Earth where signals take 45 minutes to travel one way. This is an engineering challenge that dwarfs anything we have attempted in space exploration. The Galileo mission in the 1990s gave us tantalizing data but could not get close enough to answer the key questions. The upcoming Europa Clipper mission, launched by NASA in October of 2024, will fly past Europa dozens of times and conduct the most detailed survey of the Moon ever attempted, mapping the surface, analyzing the composition, measuring the magnetic field, studying the plumes if it can catch them. But even Europa Clipper will not land. Even Europa Clipper will not drill. The question of life in Europa's ocean may take generations of spacecraft and decades of missions to answer, and there is something both humbling and thrilling about that. We are at the very beginning of this story. Ask yourself, how patient are you? Truly patient? When it comes to one of the most important questions in the history of science, are we alone in the universe? How willing are you to wait years, decades, a lifetime for the answer? Because that is what exploring Europa may require. The 13th mystery is one that exists at the intersection of science and philosophy, and it is this. What would it mean for humanity if we found life on Europa? Not just scientifically, but culturally, spiritually, existentially. We have lived for all of recorded human history as the only known life in the universe. Every religion, every philosophy, every mythology, every understanding of what it means to be human has developed in the context of a cosmos that appeared, to us, to be empty of other life. If we find even a single bacterium in Europa's ocean, even a single living cell with a metabolism and a genome, however alien, that changes everything. It does not just add one more data point to our understanding of biology. It transforms the entire question of what life is, what the universe is for, and what our place in it might be. The discovery of life on Europa would be, without exaggeration, the most significant discovery in the history of human civilization. It would make the Copernican revolution, the discovery of evolution, the invention of quantum mechanics look like footnotes. It would be the moment that the universe stopped being a monologue and became a conversation, even if the other participant is a microbe that has never heard of us and never will. The 14th mystery is about the possibility of contamination, and this cuts in both directions. The first concern is forward contamination. The possibility that a spacecraft we send to Europa might carry Earth microbes that could somehow survive the journey and contaminate the Europan ocean, making it impossible to ever know whether any life we find is truly Europan or merely hitchhiked from Earth. This is why space agencies spend extraordinary amounts of effort sterilizing spacecraft before launch. But sterilization is never perfect, and some of the hardiest microbes on Earth, the ones called extremophiles, might be able to survive both the journey through space and the harsh conditions of Europa's radiation environment. The second concern is back contamination. The possibility that if any material from Europa, say, a sample collected from the plumes, is brought back to Earth, it might carry something that our biosphere has no defense against. This is a concern that science fiction loves, but it is one that serious scientists take seriously too, not because they think Europa is likely to have predatory microbes waiting to invade Earth, but because prudence about things we do not understand is a virtue, not a paranoia. The 15th mystery is about language, communication, and the possibility of something we are almost afraid to name. Let me be clear, there is no evidence that anything in Europa's ocean communicates. There is no evidence of intelligence, of social behavior, of anything beyond the possibility of microbial life, and even that is speculative. But the question of what would happen if Europa's ocean contained something complex enough to behave, to move with apparent purpose, to respond to its environment in ways that exceed simple chemistry, that question is worth asking because the framework we have for detecting life, for recognizing it, is based almost entirely on what life on Earth looks like. A Europan organism might process information in ways utterly unlike a nervous system. It might move in ways we would not recognize as locomotion. It might reproduce using mechanisms we have never conceived of. The challenge of recognizing alien life as life, if it exists and if it is sufficiently different from us, is one of the most profound and underappreciated problems in astrobiology. We might fly through a plume full of Europan biology and miss it entirely because we were looking for the wrong molecules. The 16th mystery is geological, and it is about whether Europa has plate tectonics. On Earth, the movement of tectonic plates is one of the major drivers of the carbon cycle, chemical exchange between the mantle and the surface, and ultimately the habitability of the planet. If Europa has something analogous, if its ice shell moves in ways similar to how Earth's tectonic plates move, recycling material between the ocean and the surface and back again, then the chemical exchange between Europa's different layers could be far more active and far more complex than we currently estimate. There is some evidence, in the patterns of Europa's surface features, that something like subduction, where one section of ice slides beneath another, carrying surface material downward, may be occurring. But the evidence is disputed, and the mechanism is unclear. Ice tectonics, if it exists on Europa, would operate by different physical laws than rock tectonics on Earth, and working out the details requires both better observational data and more sophisticated theoretical models than we currently have. The 17th mystery is about what we call biosignatures, the chemical, physical, or visual signatures that would tell us, unmistakably, that life is present. On Earth, we know what to look for because we have life everywhere to study. The ratio of certain isotopes of carbon is altered by biological processes. The presence of certain organic molecules, in certain configurations, indicates biological synthesis. Patterns of gas exchange, oxygen, methane, nitrous oxide, reflect metabolic activity. But all of these biosignatures are based on Earth life, and they may not apply to Europa. Europan life, if it exists, may use different chemical pathways, may produce different metabolic byproducts, may alter its environment in ways we have never catalogued. Designing instruments that can detect biosignatures from a genuinely alien biology, when we do not know what that biology looks like, is like trying to design a filter to catch an animal you have never seen, using only nets designed for animals, you know. You might catch it, you might not. It depends on how similar the unknown animal is to the known ones. And the honest answer is, we have no idea. The 18th mystery is about sound, or rather, about what passes for sound in an ocean with no ears to hear it. Europa's ocean is a liquid medium, and like all liquid media, it transmits pressure waves, which means, in a functional sense, that it is an acoustic environment. Things make sounds in it. Hydrothermal vents rumble and hiss. Ice above cracks and settles. Chemical reactions release energy in bursts that propagate through the water. If anything in Europa's ocean has evolved sensory apparatus capable of detecting these pressure waves, something like what we would call hearing, then the acoustic landscape of Europa's ocean would be the medium through which it experiences its world. It would hear the groan of the ice above. It would hear the whisper of the hydrothermal vents below. It would hear the approach of whatever passes for predators, or prey, or simply neighbors, in the dark water of an ocean sealed from the universe by 4 miles of ice and 1 billion years of silence. This is speculation, clearly profound speculation, but it is speculation grounded in real physics, in real biology, and in the real question of what sensory modalities make sense in an environment with no light and abundant pressure waves. And there is something deeply haunting about it, isn't there? The idea of something listening, in the dark, in a frozen world, to a world it can only hear because it cannot see. Let me pause here and invite you to close your eyes for a moment. Picture an ocean. Not the Atlantic or the Pacific with their surfboards and their container ships and their salt smell that you know from childhood vacations. Picture an ocean that has never known sunlight. An ocean covered by a roof of ice so thick that nothing from outside has ever penetrated it. An ocean that has been running, in silence and in darkness, for perhaps 1 billion years. And somewhere in that ocean, perhaps near the warm floor where the rock meets the water, perhaps in the middle layers where the chemistry creates unexpected gradients, perhaps near the underside of the ice where the ceiling offers its own strange microenvironment, something is alive. You don't know what it looks like. You don't know how it thinks, or whether it thinks. You don't know whether it is aware of anything beyond its immediate chemical neighborhood. But it is alive in the same sense that you are alive. It takes in energy, it processes it, it grows, it reproduces, it responds to its world. It has done this, in an unbroken chain, for longer than multicellular life has existed on Earth. And it has never, in all that time, encountered anything from outside its ocean. Until we arrive. The 19th mystery is about the future, specifically about what happens when Europa's tidal heating eventually changes. Jupiter's grip on its moons is not static. The Laplace resonance between Io, Europa, and Ganymede is a dynamic system, and over very long timescales, it evolves. Io is currently the most volcanically active body in the solar system, heated so intensely by tidal forces that its surface is a landscape of erupting volcanoes and lakes of liquid sulfur. Europa is less intensely heated than Io, but more than Ganymede, which is in turn more than Callisto, the outermost of the 4 large moons. This gradient exists because of where each moon sits in the resonance chain, and as the resonance slowly evolves, the heating distribution may change. On timescales of billions of years, Europa's tidal heating may increase, decrease, or shift in distribution. Its ice may thicken or thin. Its ocean may grow warmer or colder. The chemistry at the seafloor may intensify or diminish. If life exists in Europa's ocean, it has already survived whatever changes have occurred over the lifetime of the solar system. But the future is uncertain, and the stability of Europa's ocean over the next few billion years is not guaranteed. Life on Europa, if it exists, may be living on borrowed time, or it may have billions more years ahead of it. We genuinely do not know. The 20th mystery is one that sits at the edge of scientific credibility, and I want to be very clear that this is speculative. But it is a speculation that serious scientists have considered, because the implications are too significant to ignore. It is the question of panspermia. The idea, formerly known as lithopanspermia, is that life can travel between planetary bodies inside rocks ejected by impacts. When an asteroid or comet hits a body with enough force, it can eject surface material at escape velocity, fast enough to leave the body's gravity well entirely and travel through space. This material, if it contains microbes, could theoretically transport life from one body to another. On Earth, we have found meteorites from Mars, rocks blasted off the Martian surface that eventually landed on Earth after wandering through space for millions of years. Could microbes survive this journey? The answer is, possibly, in some cases, for the hardiest organisms. Now, here is the thought experiment. If life originated on Earth billions of years ago, and if the early solar system was an active place full of impacts and ejected material, could some of that material have reached Europa? Could Earth life have seeded Europa's ocean in the distant past? Or, and this is the version that really keeps you up at night, could it work the other way? Could material from Europa, ejected by an impact, have landed on early Earth? Could life on Earth have a Europan ancestor? This is not a hypothesis with strong evidence behind it, and most astrobiologists would greet it with healthy skepticism. But it is a possibility that has not been formally ruled out, and in science, a possibility that has not been ruled out deserves to be taken seriously, examined carefully, and, if the evidence warrants, discussed openly. The 21st mystery is about what we will do with the answer, not the scientific implications, which we have touched on, but the human implications, the cultural, political, societal implications. When Europa Clipper begins returning data, when future missions begin to tease apart the chemistry of Europa's plumes and the structure of its ocean, we will be building, piece by piece, a picture of a world. And if that picture includes biological signatures, if the instruments return data that says, this chemistry is consistent with life, this molecular pattern is what biology makes and not what geology makes alone, then we will be standing at the edge of the most important announcement in human history, and we will have to decide how to make it. Who tells the world? How do you communicate a discovery this large to people who have been raised in a civilization that has never encountered another living world? How do you prevent panic, or euphoria, or the kind of societal disruption that comes when a belief system that has been stable for generations is suddenly overturned? These are not scientific questions. They are human questions. And the scientific community, to its credit, has been thinking about them. The field of SETI, Search for Extraterrestrial Intelligence, has protocols for announcements, and the discipline of astrobiology has been grappling with the question of public communication for years. But protocols are not the same as preparedness, and the truth is that no plan we make in advance can fully account for the earthquake that would follow a confirmed detection of life beyond Earth. The 22nd mystery, and the one I want to leave you with, is perhaps the most intimate and the most universal of them all. It is the mystery of what Europa's ocean tells us about ourselves, about why we look up, about why we spend billions of dollars and decades of human life and extraordinary ingenuity trying to reach a frozen moon hundreds of millions of miles away and peer beneath its ice. We are not doing this only for scientific knowledge. We are not doing this only because we want to know if we are alone. We are doing this because we are the kind of creatures who ask questions. We are the kind of creatures who look at the night sky and feel something. Call it wonder, call it longing, call it the peculiar human emotion that has no name, but that you feel when you stand under stars and realize that they are not just lights but entire worlds, entire stories, entire possibilities. We look at Europa because it is there, yes, but we also look at Europa because it mirrors something back at us. The possibility of life in its ocean is not just a scientific hypothesis. It is a reflection of our deepest hope that we are not unique. That life is not an accident that happened once on one unremarkable blue planet and stopped there. That the universe is not empty of meaning but full of it, full of biology and chemistry and evolution and experience and, possibly, something like wonder in places we have never imagined. Let's go deeper now, because the mysteries of Europa do not exist in isolation. They are woven into a broader tapestry of questions about our solar system, our galaxy, and the nature of life itself. And pulling any single thread leads you somewhere extraordinary. Consider the role of water in the universe. Water, 2 hydrogen atoms and 1 oxygen atom, H2O, the simplest and most abundant molecule in the cosmos after hydrogen and helium themselves, is a molecule of almost magical properties. It is an extraordinary solvent, able to dissolve more different substances than any other common liquid. It has high heat capacity, meaning it resists temperature change and stabilizes the environments it fills. It expands when it freezes, a property so unusual that most liquids do the opposite, which is why ice floats on water rather than sinking, a property that has profound consequences for the habitability of water bodies on Earth. It is transparent to visible light but opaque to many other wavelengths, creating a natural greenhouse effect. It participates in more chemical reactions than almost any other molecule. And it is, on Earth at least, absolutely indispensable for life as we know it. Every living cell on Earth is essentially a bag of water with chemistry happening inside it. DNA requires water to maintain its structure. Proteins fold in water. Metabolic reactions occur in water. We are, quite literally, creatures of water. Now consider this. The universe is full of water. Comets are rich in water ice. The outer regions of planetary systems are dominated by ice, water ice, methane ice, ammonia ice. The grand architecture of our solar system divides into the rocky, dry inner worlds and the icy, water-rich outer worlds, separated by the frost line, the distance from the sun beyond which water ice can persist. Europa sits well beyond the frost line, and it is drenched in water, not just drenched on the surface, but harboring a deep, persistent, global liquid ocean driven by tidal forces rather than solar energy. And Europa is not unique in this. Ganymede, the largest moon in the solar system, likely has a subsurface ocean. Callisto probably does too. Enceladus, a moon of Saturn, has an ocean and has been confirmed to be actively venting water vapor and organics into space through its south polar plumes. Data that was collected by the Cassini spacecraft and that remains one of the most extraordinary datasets in the history of planetary science. Titan, another moon of Saturn, has lakes and seas, not of water, but of liquid methane and ethane, and may have a subsurface ocean as well. The universe is not stingy with water. The universe is extravagant with it. And if water is the medium of life, then the universe may be extravagantly full of the possibility of life. This realization has transformed astrobiology over the past 2 decades. The old model of the habitable zone, the narrow band around a star where a planet can have liquid water on its surface, has been recognized as far too conservative. Tidal heating, as demonstrated by Europa, can maintain liquid water oceans far outside the traditional habitable zone. Radioactive decay in the interior of rocky worlds can generate heat that sustains subsurface liquid water indefinitely. The universe has found far more ways to keep water liquid than the simple model of sunlight and surface temperature would suggest. This means that the number of potentially habitable worlds in our galaxy, and in the universe, may be orders of magnitude larger than we thought a generation ago. Not tens of thousands of candidate worlds, but billions. Not a rare exception, but a potential norm. And if life can arise in a subsurface ocean, sealed beneath miles of ice, driven by tidal or radiogenic heating, far from any star, then the universe is perhaps the most hospitable place imaginable for biology. Every icy moon in every solar system around every one of the hundreds of billions of stars in our galaxy may be hiding an ocean. And every one of those oceans may be running the same experiment Europa is running. The experiment of what happens when you put water and chemistry and energy together and wait. Let's talk about the Galileo spacecraft, because it is the single most important source of data we have about Europa, and its story is one of the most poignant in the history of space exploration. Galileo was launched in 1989, made its way to Jupiter over a 6-year journey that involved gravity assists from Venus and Earth, and entered orbit around Jupiter in December of 1995. Over the next 8 years, It conducted 35 orbits of Jupiter and made multiple close flybys of the Galilean moons, including Europa, Ganymede, Callisto, and the volcanic hellscape of Io. The data it returned was transformative. Its magnetometer measured perturbations in Jupiter's magnetic field near Europa that were consistent with the presence of a global, electrically conductive layer, which is precisely what a salty ocean would produce. This was not proof of an ocean, but it was the strongest evidence yet, and it converted most planetary scientists from skeptics to believers. Galileo also imaged Europa's surface at unprecedented resolution, revealing the chaos terrain, the Linnea system, and the young, renewed surface that we discussed earlier. It sniffed the Europan environment with its mass spectrometer and found hints of salts and sulfuric acid compounds. It measured Europa's gravity field with enough precision to constrain the interior structure. But Galileo was a limited mission in important ways. Its high-gain antenna, the large dish that was supposed to send data back to Earth at high speed, failed to fully open after launch, leaving the spacecraft transmitting at a tiny fraction of its planned data rate. Scientists had to make painful choices about what data to prioritize, knowing that the transmission bandwidth was precious. Entire datasets were never recorded or transmitted because there was simply not enough time and bandwidth. And in 2003, as its fuel ran low and its electronics were increasingly damaged by the Jovian radiation environment, NASA deliberately flew Galileo into Jupiter's atmosphere, destroying it, partly to avoid any possibility that the spacecraft could accidentally contaminate Europa with Earth microbes. Even in death, Galileo was managed with the care and responsibility that the possibility of Europan life demands. There is something deeply moving about the story of Galileo. A spacecraft launched before most of the people reading this were born, carrying instruments designed in an era before the internet, traveling for 6 years to reach its destination, operating for 8 more years despite a crippled antenna, and delivering some of the most important scientific data of the 20th century, all while being slowly killed by the radiation of the planet it was studying. And then, in its final moments, diving into Jupiter's clouds to ensure that whatever it might carry from Earth could never contaminate the world below. It is, in the best possible sense, a human story. A story of perseverance, of sacrifice, and of the kind of careful, responsible curiosity that science demands. Now, in October of 2024, humanity launched a worthy successor. Europa Clipper is the largest planetary science spacecraft NASA has ever built, with solar panels that stretch 30 meters from tip to tip, because at Jupiter's distance from the Sun, the sunlight is 25 times weaker than at Earth, and the spacecraft needs those enormous panels to generate enough power for its instruments. Europa Clipper carries a sophisticated suite of instruments including cameras, ice-penetrating radar, a magnetometer, a spectrometer, a thermal imager, and instruments designed to analyze the composition of material in Europa's thin atmosphere and, if it encounters them, in the plumes. It will conduct 49 close flybys of Europa over its primary mission, swooping as close as 25 kilometers to the surface, gathering data on the ice shell's thickness, the ocean salinity and temperature, the chemistry of the surface and atmosphere, and the location and properties of any plumes. Europa Clipper will not tell us whether life exists in Europa's ocean. Let's be honest about that. No instrument currently in existence can make that determination from the outside. But Europa Clipper will tell us whether Europa's ocean is habitable, whether it has the right temperature, the right chemistry, the right energy sources, the right conditions to support life as we understand it. And if it is habitable, then the next mission, a lander, perhaps eventually a submarine, becomes one of the most urgently important scientific endeavors in human history. Think about the timeline for a moment. Europa Clipper will arrive at Jupiter in 2030. Its primary mission will last until around 2034. Data analysis will take years after that. A follow-up lander mission, if approved and funded, would take another decade or more to reach Europa. We are talking about answers in the 2040s, at the earliest, for questions that we are asking in the 2020s. This is the pace of solar system exploration, measured not in news cycles but in generations. And there is something profoundly important about that. In a world that often demands instant gratification, instant answers, and instant results, The exploration of Europa asks us to be patient in a way that we are barely accustomed to. It asks us to invest in something whose payoff we may not live to see. It asks us to believe that the question is worth asking even when the answer is decades away. Is that kind of patience still possible for us? Is that kind of investment in the long future something our civilization can sustain? These are not rhetorical questions. They are real ones, and the fate of Europa exploration depends on how we answer them. Let's return now to the surface of Europa, because there is more there than linear and chaos terrain, and the details are extraordinary. One of the strangest features of Europa's surface is what scientists call lenticulae, Latin for small lenses, which are small, roughly circular features, typically a few kilometers across, that dot parts of Europa's surface. Some are raised domes, some are pits, some are flat spots with disrupted surroundings. They look, at low resolution, a bit like acne on the face of the moon, but the processes that create them are far more interesting than that comparison suggests. The leading hypothesis is that lenticulae are formed by diapirs, buoyant blobs of warmer ice rising from deep within the ice shell, like the blobs of colored wax rising in a lava lamp. If this is correct, it means that the ice shell is not static and homogeneous, but is actively convecting. Warm ice rising, cold ice sinking, with plumes of warm ice moving from the base of the shell toward the surface. This convective overturn would mix material between the ocean and the surface over geological timescales, creating the chemical exchange that could be so important for habitability. But there is another hypothesis for lenticulae that is more dramatic. Some researchers have proposed that they form not through ice convection but through the direct intrusion of liquid water, that in some cases, actual ocean water pushes up through the ice shell, creating a pocket of liquid water within or beneath the ice that then slowly refreezes. If this is correct, Europa's ice shell may be riddled with pockets and layers of liquid water at various depths, creating a complex, three-dimensional hydrological system within the ice itself, not just at the base. These liquid water lenses, if they exist, would be environments with their own chemistry, their own physical conditions, and their own potential for biology. The possibility of habitable niches, not just in the ocean below but within the ice itself, is one of the more exciting frontiers in Europa science. And here is a thought that crystallizes all of this into something almost impossibly poignant. The surface of Europa is one of the most radiation-hostile environments in the solar system. Anything on the surface is bombarded constantly by energetic particles from Jupiter's magnetic field. Nothing, as far as we know, could survive on Europa's surface for long. But within the ice, shielded by even a few meters of overlying material, the radiation drops to manageable levels. And within the ocean below, shielded by kilometers of ice, the radiation is essentially zero. Europa's ocean may be one of the most radiation-sheltered environments in the outer solar system, precisely because it is so deeply buried. The very thickness of the ice that makes exploration so challenging is also what might make the ocean such a safe harbor for life. Safe harbor. That is an interesting phrase to use about a world we have never visited, an ocean we have never touched, and a life we have not yet found. But it resonates, because that is what Europa's ocean may be. A harbor, a refuge. A place where the laws of chemistry and physics conspire to create and maintain conditions in which life could shelter and grow, shielded from the cosmic violence of space and the crushing radiation of a giant planet, sustained by the endless heartbeat of tidal forces, warm in its own quiet way at the bottom where the rock exhales heat into the water, dark and ancient and patient in a way that nothing on Earth's surface can quite be. Now let's talk about what we might actually find, if we ever do reach Europa's ocean. Let's be rigorous but imaginative, because the science of what might exist there is both more specific and more uncertain than most people realize. The most conservative possibility, and still the one that most astrobiologists would bet on if forced to choose, is microbial life. Simple organisms, analogous to Earth's archaea or bacteria, perhaps using chemical energy rather than sunlight, perhaps growing in biofilms on the hydrothermal vent surfaces or floating freely in the water column, perhaps forming symbiotic communities that cycle nutrients between different chemical niches. On Earth, microbial life has been found in hydrothermal vent systems at the bottom of the Pacific and Atlantic Oceans, and the chemistry there is, in many ways, analogous to what we expect at the bottom of Europa's ocean. The black smokers and white smokers of Earth's ocean floor host ecosystems of extraordinary diversity and productivity, all built on chemosynthesis rather than photosynthesis. Europa's seafloor may have its own version of these systems, and if it does, the case for microbial life there becomes very strong. But what if we look beyond microbes? What if we entertain, as a serious scientific speculation rather than a fantasy, the possibility of something more complex? On Earth, the transition from microbial to complex multicellular life took about 3 billion years, and it seems to have required specific conditions, including a significant increase in atmospheric oxygen from the photosynthetic activity of cyanobacteria. Europa has no sunlight reaching its ocean, so photosynthesis is impossible there. But tidal forces, chemical gradients, and hydrothermal activity could generate other energy gradients. And it is not inconceivable that a sufficiently complex chemistry could drive the evolution of something beyond the microbial. This is speculative. This is very speculative. But it is not absurd, and the scientific community has been willing to entertain it, at least in informal discussions and speculative papers, with the appropriate caveats and qualifications. If complex life did evolve in Europa's ocean, what would it look like? This is where we enter territory that is genuinely beyond our current science, and where imagination and biology meet in uncomfortable and wonderful ways. The absence of light would mean that any visual system analogous to eyes would be either vestigial or adapted to detect bioluminescence, the production of light by living organisms. Bioluminescence is extraordinarily common on Earth in the deep ocean, used for communication, for luring prey, for camouflage, for a dozen other functions. In an ocean with no ambient light, bioluminescence becomes the only visual medium, and evolution might drive organisms to develop increasingly sophisticated bioluminescent displays and increasingly sensitive light detection systems. An ocean full of bioluminescent organisms, flickering and glowing in the dark, would be one of the most beautiful things imaginable, and also one of the most alien. In the absence of light, other senses become paramount. Pressure sensitivity, the ability to detect waves and currents in the water, would be crucial for navigation, for detecting prey and predators, for communicating with other members of the same species. Chemoreception, the ability to detect chemical gradients in the water, would be vital for finding food, for assessing the environment, for reproductive signaling. These are senses that Earth organisms have too, but in Europa's ocean, they might be far more highly developed, far more central to the organism's experience of its world, than they are in any Earth creature that also has vision and hearing in the conventional sense. The gravitational field of Europa is about 13% of Earth's, which means that in the water of Europa's ocean, the effective weight of objects is very low. This would influence the evolution of body plans and locomotion in ways that are difficult to predict. On Earth, large aquatic animals are shaped by the interplay of buoyancy, drag, and the need to move efficiently through water. In Europa's ocean, with lower gravity, the mechanics would be different, and the body plans that evolution arrived at might be correspondingly different. Something large enough to be seen with the naked eye in Europa's ocean might look nothing like a fish, or a jellyfish, or any other familiar form. It might be something genuinely new, genuinely alien, genuinely outside the categories our minds have built from a lifetime of encountering Earth life. And then there is the question of the ice-water interface, the underside of the ice ceiling that covers Europa's ocean. On Earth, the undersides of sea ice in polar regions are home to communities of ice algae, krill, and other organisms that exploit the unique conditions there. The availability of sunlight filtered through the ice, the concentration of nutrients, the physical structure of the ice itself as a substrate for attachment and growth. In Europa's ocean, there is no sunlight coming through the ice, but there are other potential resources at the ice-water interface. The interface itself creates chemical gradients. Material coming down from the radiation-processed surface ice may provide oxidants. The ice provides a solid substrate. Some researchers have speculated that the underside of Europa's ice shell might be a unique ecological niche, a cold, dark, chemically complex environment that could support its own community of organisms, different from those near the hydrothermal vents below. Imagine two communities of life, separated by 60 to 100 kilometers of dark water, having evolved in complete isolation from each other. One near the warm, chemically energetic seafloor, the other in the cold and chemically oxidized environment beneath the ice ceiling. Would they be recognizably related to each other, sharing a common ancestor from early in Europa's biological history? Or would they have diverged so completely, driven by such different selective pressures, that they would look as different from each other as plants and animals on Earth look different from each other? Or, and this is the strangest possibility of all, could they have originated independently, arising from separate chemical beginnings in different parts of the ocean, and representing truly separate origins of life within a single world? This last scenario, two independent origins of life within the same ocean, is a thought experiment that staggers the imagination. Life on Earth has a single origin. Every living thing on our planet, from bacteria to sequoia trees to blue whales to human beings, shares a common ancestor and a common genetic code. The universality of the genetic code is one of the strongest pieces of evidence we have that life originated once on Earth and diversified from there. But on Europa, with a vast, isolated, chemically diverse ocean, the possibility of separate origins in separate chemical niches is not impossible. If we ever found two distinct forms of life in Europa's ocean, with different biochemistries, different genetic codes, if they have genetic codes at all, different fundamental chemistry, that would not just double the discovery. It would transform our understanding of how common life is. It would suggest that life is not just possible but probable, not just lucky but nearly inevitable, wherever the right conditions persist for long enough. Let us talk for a moment about the history of how we came to understand Europa, because that history is itself a story of remarkable discoveries made by people of remarkable dedication, and it is a story that very few people know fully. The four large moons of Jupiter, Io, Europa, Ganymede, and Callisto, were discovered by Galileo Galilei in January of 1610, using a telescope of his own construction, and their discovery was revolutionary in ways that go far beyond astronomy. For centuries, the dominant model of the cosmos held that everything in the universe revolved around the Earth. The geocentric model endorsed by the Church and embedded in the philosophical tradition of Aristotle. When Galileo pointed his telescope at Jupiter and saw four small points of light moving around it night after night, he realized that not everything in the universe revolved around the Earth. Here were four objects, moons, clearly revolving around something that was not the Earth. This was among the most powerful observational arguments for the heliocentric model of the solar system, and it contributed to the Copernican revolution that placed the Sun, rather than the Earth, at the center of our cosmic picture. The moons Galileo discovered were called the Galilean moons in his honor, and they have been observed and studied ever since. But for 3.5 centuries they were nothing more than points of light in telescopes, their surfaces unresolved, their nature unknown. It was not until the Pioneer 10 and 11 missions in the early 1970s, and then the spectacular Voyager 1 and 2 flybys in 1979, that we got our first close-up images of the Galilean moons and realized that each one was a world unto itself. Io, covered in active volcanoes, was unlike anything anyone had predicted. Ganymede, the largest, had a surface showing signs of ancient geological activity. Callisto was densely cratered, preserved from the early solar system like a fossil. And Europa was smooth, strange, covered in those enigmatic reddish lines, almost devoid of craters, its surface gleaming like a polished ball bearing. The Voyager images were low resolution by modern standards, but they were enough to set scientists thinking. Why is Europa so smooth? What is going on beneath that ice? The idea that Europa might have a subsurface ocean had been proposed even before the Voyager flybys, in a 1979 paper by Stanton Peele, Patrick Casson, and Ray Reynolds, who predicted that tidal heating from Jupiter would generate significant internal heat in Io, a prediction that was dramatically confirmed when Voyager 1 discovered active volcanoes there. The same reasoning, applied to Europa, suggested that tidal heating would keep its interior warm enough for liquid water. But it was the Galileo mission, from 1995 to 2003, that provided the definitive magnetic evidence for the ocean and transformed the subsurface ocean from a theoretical possibility to a near certainty. And it was the work of scientists like Brittany Schmidt, Don Blankenship, and their colleagues who began using ice-penetrating radar techniques developed for studying Earth's own ice sheets in Greenland and Antarctica, and adapting them for Europa, developing the conceptual and technical frameworks for how to study an ocean we cannot reach with our current technology. These are real scientists doing real work, motivated not by the certainty of finding life, but by the certainty that the question deserves to be answered, that Europa deserves to be understood, that the universe owes us no easy answers, but that careful, patient, rigorous science can find them anyway. There is a particular kind of heroism in spending a career studying something you may never get to visit, using instruments that may not be built in your lifetime to investigate questions that may not be answered until after you are gone. The scientists who work on Europa are not doing it for glory or for quick results. They are doing it because the question matters, because the answer, whatever it is, will change everything, and because someone has to be the one to do the work that makes the answer possible. The Cassini mission's discovery of plumes at Enceladus, Saturn's moon, in 2005, changed the conversation about icy moon oceans in a way that galvanized the entire field. Enceladus is a small moon, much smaller than Europa, but it has a confirmed, active ocean venting through its south pole in dramatic plumes of water vapor, ice particles, and organic compounds. Cassini flew through those plumes and detected hydrogen, carbon dioxide, methane, and simple organic molecules. The presence of hydrogen in particular was significant, because it is consistent with hydrothermal reactions at the seafloor, hot water reacting with rock in a process called serpentinization, which produces hydrogen and is a potential energy source for microbial life. The discovery made Enceladus the most immediately accessible target for ocean sampling in the solar system, and it raised the possibility that any mission designed to fly through its plumes could, in principle, detect biosignatures without ever having to land or drill. Europa's plumes, if they are as active and accessible as Enceladus's, offer the same opportunity. And while Enceladus's plumes were discovered by a spacecraft already in Saturn orbit and able to make multiple passes, Europa's are harder to catch. The geometry of Europa's orbit makes it difficult to fly through a plume even if you know where to look, and the plumes seem to be intermittent, making their timing and location unpredictable. But Europa Clipper's instruments have been specifically designed with plume encounter in mind, and if any plumes are active during its flybys, the spacecraft will be ready. Here is something worth emphasizing, because it is often lost in the broader narrative. The search for life on Europa is not a peripheral or fringe activity of the scientific community. It is one of the most highly prioritized scientific endeavors in the world. The 2023 Planetary Science and Astrobiology Decadal Survey, the document produced every 10 years by the National Academies of Sciences, Engineering, and Medicine that sets the priorities for NASA's planetary science program, identified Europa Clipper and a potential Europa lander as top priorities for the coming decade. The scientific community has voted, repeatedly and clearly, that Europa is one of the most important places in the solar system to study, and that the search for life there is one of the most important scientific questions of our time. This is not a niche obsession. This is the mainstream of planetary science. Let's now explore a perspective that rarely gets discussed in the popular accounts of Europa: the economic, political, and societal dimensions of exploring it. The Europa Clipper mission cost approximately $5 billion. This is a staggering sum of money, and critics quite reasonably ask whether it should be spent on other priorities: education, healthcare, poverty alleviation, climate change mitigation. These are legitimate questions, and they deserve honest answers. The honest answer is that the investment in fundamental science and space exploration has historically paid dividends in ways that are impossible to predict in advance. The technologies developed for space exploration have found applications in medicine, communications, material science, environmental monitoring, and dozens of other fields. GPS, which runs the global economy in ways most people take completely for granted, came directly from satellite technology developed for space exploration. The sensors used in modern medical imaging owe their development in part to the radiation detectors built for space science. The computational algorithms used for digital photography were pioneered by the teams that processed images from planetary spacecraft. But beyond the economic argument, there is a deeper case. Civilizations that do not invest in understanding their universe, that confine themselves to the immediately practical and the immediately profitable, impoverish themselves in ways that are harder to measure but no less real. The questions Europa poses about life, about the universe, about what we are not luxuries. They are the kind of questions that define what a civilization believes itself to be. They are the questions that separate a civilization that looks outward, with curiosity and humility, from one that turns inward and closes its eyes. Now, let's consider the political dimensions. The Outer Space Treaty of 1967, which forms the basis of international space law, prohibits the appropriation of celestial bodies by any nation and requires parties to avoid the harmful contamination of space bodies. These provisions apply directly to Europa exploration, and they create a complex web of obligations and uncertainties. If a private company, say SpaceX or a future commercial space entity, wants to send a mission to Europa, what rules apply? Who is responsible for ensuring planetary protection? Who has the authority to declare whether a detected biosignature constitutes a discovery of life, and what the implications of that declaration are? These are not hypothetical questions for the distant future. They are real questions for the present, as the commercial space sector grows and the gap between what governments regulate and what technology enables grows with it. And there is a geopolitical dimension too. China's space agency has announced ambitions to explore the outer solar system, including Jupiter and its moons. Europe's ESA is operating the JUICE mission, Jupiter Icy Moons Explorer, which arrived at Jupiter in 2031 in the timeline of these explorations and is focused primarily on Ganymede but will also study Europa. The exploration of Europa is not just an American story. It is a human story, being written simultaneously by multiple actors with different priorities, different timelines, and different political contexts. The governance of what happens if life is found, or if something ambiguous but suggestive is found, is a question that the international community has not yet adequately addressed. Let's shift now to a purely speculative territory that scientists keep at arm's length in formal publications, but that they allow themselves to explore in hallway conversations and late-night discussions at conferences. What if Europa's ocean contains not just life, but organized behavior? Not intelligence, necessarily, not anything that reads and writes and builds cities, but organized behavior, the kind of thing we see in social insects, in schooling fish, in migratory birds, in any system where individual organisms coordinate their actions in ways that produce emergent group-level patterns. Collective behavior in biological systems arises from simple rules applied consistently by individual agents, and it can produce extraordinarily complex outcomes without any individual agent understanding the whole. A colony of ants does not need an architect to build an intricate nest. A school of fish does not need a choreographer to execute its breathtaking synchronized evasion of a predator. Collective behavior is one of biology's most powerful tools for producing order from simplicity, and there is no reason it could not arise in Europa's ocean, given sufficient time and sufficient selective pressure. If there are organisms in Europa's ocean that form communities, that coordinate their chemistry, their movement, their reproduction in ways that produce group-level behavior, then Europa's ocean is not just an ecosystem but a society of sorts. Not a human society, not even a vertebrate society, but a system in which individual agents relate to each other in structured, patterned ways. And detecting that kind of organized behavior, from a spacecraft flying past a frozen moon, is an engineering and scientific challenge that we have barely begun to think about. There is something philosophically vertiginous about this possibility. We send probes to other worlds to look for life, and we build those probes with instruments designed to detect the chemical signatures of life as we understand it. But what if life, in some of its forms, is more about behavior and organization than about specific chemistry? What if a sufficiently alien form of life is recognizable not through its molecules but through its patterns? We detect information, not just matter. We see structure, not just substance. This is the kind of question that sits at the boundary of biology, information theory, and philosophy, and Europa, by forcing us to think about life in contexts radically different from the ones we evolved in, pushes us to that boundary whether we are ready or not. Now I want to take a step back and think about Europa in the context of what we call the Fermi paradox. The question of why, if the universe is so vast and so old and life might be so common, we have not yet heard from anyone else. If oceans like Europa's are common throughout the galaxy, and given the physics of tidal heating and the abundance of water ice in the outer solar system, there is good reason to think they might be, then the galaxy may be teeming with life in subsurface oceans. But here is the thing: subsurface ocean life, even if it exists everywhere, is invisible to us. It produces no radio signals. It sends no spacecraft into space. It does not alter the spectrum of its host moon's atmosphere in detectable ways. A galaxy full of microbial life in subsurface oceans would look, from the outside, exactly like a lifeless galaxy. The Fermi paradox assumes that life, given enough time, will produce detectable signals. But what if most life in the universe is sealed beneath miles of ice, running on chemistry in the dark, with no access to space and no ability to produce signals we could detect? What if the universe is full of life, and we are simply looking in the wrong way, with the wrong instruments, at the wrong scale? This is not a resolution to the Fermi paradox. It is a complication of it. And complicating the Fermi paradox, making it richer and more nuanced, is exactly what the study of Europa does. It forces us to question our assumptions, to examine the frameworks we use to ask questions about the universe, and to acknowledge that our answers are only as good as our assumptions, and our assumptions may be very, very limited. Consider the concept of the Great Filter, which was proposed by economist Robin Hanson in 1998 as a way of thinking about why we don't see evidence of intelligent life elsewhere in the universe. The Great Filter is a metaphor for whatever process, or series of processes, reduces the number of technological civilizations in the galaxy from what we might naively expect to what we actually observe, which is apparently just one, us. One possibility is that the filter is behind us, that the transition from simple chemistry to biology, or from simple life to complex multicellular life, or from multicellular life to intelligence, is so improbable that it has happened only once or a handful of times in our galaxy. If this is the case, then the discovery of simple life on Europa would be extremely bad news for humanity's long-term prospects, because it would suggest that the filter is not behind us but ahead of us, and that some catastrophic barrier lies between where we are now and where a technological civilization needs to get to in order to persist and expand. Another possibility is that the filter is ahead of us, that some technological or environmental catastrophe reliably destroys civilizations before they can become sufficiently advanced to make their presence known. In this case, finding simple life on Europa would be less alarming, but would do nothing to resolve the mystery of why we are apparently alone as a technological civilization. And there is a third possibility, which is that the filter is not a filter at all, that the universe is full of life and even of intelligence, but that intelligence, for reasons we do not understand, does not produce the kind of expansive, galaxy-colonizing civilization we might expect. Perhaps intelligence is common, but technological civilization is rare. Perhaps technological civilization is common, but long-distance space colonization is impossible or undesirable. Perhaps we simply have not been listening long enough, or in the right way, to detect signals that are already out there. Europa cannot resolve the Fermi paradox, but it can change the terms of the debate by giving us a second data point on the distribution of life in the universe, or by giving us only the absence of a second data point, which is also informative. Every world we study, every ocean we probe, every atmosphere we analyze, narrows the range of possibilities, pushes the probability distribution, gives us a better picture of what kind of universe we live in. And the picture is becoming, with every passing year and every new mission, both more vivid and more complex. Let me tell you something that rarely makes it into the popular accounts of Europa. The people who study it, the scientists, the engineers, the mission planners, the astrobiologists, many of them are not doing this work out of cold professional calculation. They are doing it because Europa captured them, the way great questions capture people, The way a particular piece of music or a particular sentence in a particular book can reach into you and rearrange something essential about who you are. Brittany Schmidt, who leads the Ice Worlds team at Cornell, has spoken publicly about her passion for the question of life in Europa's ocean in terms that go beyond professional commitment. She has described it as the question she is willing to dedicate her career to, even knowing that the answer may not come in her lifetime. Kevin Hand at the Jet Propulsion Laboratory, who wrote the book Alien Oceans, has spent decades arguing that Europa is not just scientifically important, but that it represents a moral imperative, that if there is life there, we have both a right and a responsibility to find it. Robert Pappalardo, also at JPL, has been one of the driving forces behind Europa Clipper for much of his career, shepherding the mission through the complex and often frustrating process of scientific prioritization, budget negotiations, and political review that all large NASA missions must endure. These are not distant, abstract figures. They are people who went to school, who have families and favorite foods and days when the science doesn't work and the data doesn't make sense and the funding looks uncertain, and who choose, day after day, to come back and keep asking the question. There is something deeply human about that. And it is part of what makes the story of Europa not just a story about a moon, but a story about us. Now let's think about something that is rarely framed this way, but that I think is worth framing explicitly. If we discover life on Europa, the most important immediate scientific question will not be what kind of life it is. The most important question will be whether it is related to life on Earth. Remember what we said about panspermia, the theory that life can travel between worlds and rocks ejected by impacts? If life on Europa turns out to share the same basic genetic code as life on Earth, if it uses DNA or RNA, if it uses the same 20 amino acids, if it reads the same molecular language, then we will have to seriously consider the possibility that life on Earth and life on Europa share a common origin, transported between worlds in the early solar system when impacts were more frequent and the exchange of material more common. That would be extraordinary, but it would also be somewhat less extraordinary than the alternative. If life on Europa uses a completely different biochemistry, different molecular machinery, different genetic language, different fundamental chemistry, then we will have found a second, independent origin of life, and that will be the discovery that changes everything. A second origin of life in our own solar system would mean that life is not a cosmic accident but a cosmic inevitability, that given the right conditions, it arises, it persists, it proliferates. And if it arises twice in our own modest solar system, then the implication for the rest of the galaxy, with its hundreds of billions of stars and its untold trillions of worlds, is staggering beyond calculation. Two independent origins of life in one solar system would tell us, without room for reasonable doubt, that the universe is alive. Not just has the potential for life, is alive. Right now. Everywhere conditions permit. A living universe, full of biology in 1,000 forms we have never imagined, running in the dark beneath frozen oceans and in the acid clouds of gas giants and in the subsurface of airless rocks and in places we have not yet thought to look, because we are still learning, still growing, still expanding our picture of what is possible. The prospect is dizzying, and it begins, perhaps, in an ocean sealed beneath 4 miles of ice on a moon of Jupiter, 390 million miles away, in the dark and the warmth and the chemistry and the silence. Let's talk about the role that science fiction has played in shaping our thinking about Europa, because the relationship between fiction and science is more complicated and more important than it might appear. Arthur C. Clarke, one of the most prophetic science fiction writers of the 20th century, set his 1982 novel 2010, Odyssey 2 in the Jovian system, and in it, he imagined Europa as a world being deliberately seeded with life by an alien intelligence using Jupiter itself as a new star. The novel ends with a warning message. All these worlds are yours, except Europa. Attempt no landing there. This line has become almost totemic in the Europa scientific community. A joke, a warning, and a kind of aspiration all at once. Clarke was not doing science. He was doing something science fiction does at its best, taking a scientific possibility seriously enough to follow it to its emotional and philosophical implications. He imagined a Europa that was not just a candidate for life, but a world actively protected by a superior intelligence that was nurturing that life. That is not a scientific hypothesis, but it is a way of taking the question seriously, of insisting that the answer to "are we alone" matters not just intellectually but morally. Michael Crichton's less celebrated 1987 novel Sphere, while not set on Europa, explored many of the same themes: the discovery of a deep ocean alien artifact, the psychological impact on the human beings who encounter it, the difficulty of understanding something genuinely outside our categories. Peter Watts, a marine biologist who became a science fiction writer, set much of his novel Blindsight and its sequel Echopraxia in fictional alien contexts that deliberately challenge the human-centric assumptions we bring to the question of what intelligence looks like. These writers are not doing science, but they are doing something equally important. They are preparing us, emotionally and philosophically, for discoveries that science has not yet made but that science tells us are possible. And this preparation matters, because when, not if, perhaps, but when we find evidence of life beyond Earth, the human response to that discovery will be shaped by the stories we have told ourselves in advance. Stories of fear, stories of wonder, stories of contact and misunderstanding, stories of transformation. All of these prepare us to receive a discovery that will demand the best of us, that will challenge everything we think we know, and that will require us to be bigger, more generous, more curious, and more humble than we usually allow ourselves to be. The relationship between science and story is not accidental. Human beings are narrative creatures. We understand the world through stories, we communicate through stories, we build cultures and civilizations and scientific traditions through the stories we tell about what matters and why. The story of Europa is one of the most important stories being told right now, in laboratories and spacecraft control rooms and international scientific conferences and, yes, in books and documentaries and conversations late at night when someone looks up at the stars and wonders. And the power of this story, the reason it captures people, the reason it generates both scientific urgency and popular fascination, is that it is not just a story about a moon. It is a story about us, about what we hope the universe is like, about what we fear it might be like, about the kind of courage it takes to ask questions when you know the answers might change everything. Consider for a moment the emotional weight of the following scenario. The year is 2035. Europa Clipper has completed its primary mission and returned data that suggests, strongly suggests, though the scientific community is carefully hedging its language, that Europa's ocean contains chemical signatures consistent with biological activity. Not proof, not certainty, but a pattern in the mass spectrometry data that has no known non-biological explanation. The world is waiting. Follow-up analysis is underway. The scientists are not sleeping. The press is camped outside JPL, and somewhere on the frozen surface of a moon of Jupiter, in the dark beneath miles of ice, something is happening. Something that has been happening for perhaps 1 billion years, and it has no idea that a species 390 million miles away is holding its breath. That scenario is not guaranteed. It may never happen exactly that way, or at all. But it is possible. It is within the range of outcomes that the next decade of Europa exploration might produce. And the fact that it is possible, the fact that we are, right now, in the period when the question is still open, when the answer is still unknown, when the story is still unwritten, is itself one of the most extraordinary things about being alive in this particular moment in human history. We have sent 7 billion years of Earth's geological and biological work into the future in the form of the human species. We have developed science, the most powerful tool for understanding reality that any known entity has ever produced. We have launched spacecraft to the outer solar system, and we are in the process of launching more. We stand right now on the threshold of the most important discovery in the history of our species. Not guaranteed, not certain, but possible. Possible in our lifetimes, or in the lifetimes of our children, or in the lifetimes of their children. Possible enough that extraordinary resources and extraordinary talent are being devoted to pursuing it. Possible enough that the thought keeps scientists up at night, not with anxiety but with something very close to awe. Let me bring us back to the ocean one more time. Not to the science of it, not to the speculation about it, but to the simple, overwhelming fact of it. Beneath 4 miles of ice, on a moon of Jupiter, there is an ocean. A real, liquid, global, ancient, chemically active ocean. It has been liquid probably for hundreds of millions of years, possibly for billions. It has been sealed from the universe by ice during that entire time. It has been warmed from below by the squeezing hands of Jupiter's gravity, and it has been chemically fed by the slow reaction of its water with the rock of Europa's seafloor. It has salts in it. It may have organics in it. It has energy moving through it, from the warm floor to the cold ceiling, from the ice-processed surface to the mineral-rich water below. It is, by every measure we have, the kind of place where life could exist. Whether life does exist there, whether the chemistry has crossed the astonishing threshold from self-organizing molecules to self-replicating ones, from chemistry to biology, from matter to life, we do not know. We have not been there. We have not touched the water. We have not seen what swims in it, or whether anything swims in it at all. We have looked from 390 million miles away, with spacecraft instruments and computer models and the very best tools that human ingenuity has produced, and we have said, there is probably an ocean. It is probably old. It is probably warm enough, and chemical enough, and energetic enough to support life. And that is as far as we can go for now. But for now is not forever. The spacecraft is on its way. The instruments are designed. The questions are formulated. The scientists are ready. And the ocean is there, vast, dark, ancient, patient, waiting, as it has always waited, for whatever comes next. Whether that is a robot probe, or a lander, or a drilling system, or something we have not yet imagined, or whether it is simply more waiting, more patient waiting, as it has waited for billions of years before we even arrived to ask the question. Think about that patience. An ocean that has been running for 1 billion years. 1 billion years is a number so large that it has no intuitive meaning for a species that lives for at most 100. But try this. If 1 second represents 1 year of geological time, then 1 billion years is about 32 years of seconds. Europa's ocean has been running, in this metaphor, for your entire lifetime measured in seconds. Every second of every minute of every hour of every day of every year of your life represents 1 year of that ocean's existence. And in all that time, all of those seconds, all of those years, no one has ever visited it, no instrument has ever touched it, no eye has ever seen it. It has run its chemistry in complete darkness and complete isolation, driven by the gravity of a gas giant and the thermal energy of a rocky seafloor, and whatever it has produced, whatever life, whatever complexity, whatever beauty or strangeness or simplicity, it has produced without ever knowing that somewhere in the inner solar system, on the third planet from the sun, a species of upright primates was slowly, painfully, brilliantly developing the intelligence and the tools and the curiosity to come and ask, "What are you?" We are coming. We may be closer to an answer than we have ever been, and farther from the answer than we want to be at the same time. That is the nature of exploration. That is the nature of science. That is, perhaps, the nature of the universe. Generous with possibility, parsimonious with certainty, endlessly and mysteriously itself. And somewhere in the dark, in the water, in the ancient chemistry of a frozen world, the answer is waiting. Patient as an ocean. Silent as 4 miles of ice. Alive, perhaps, in ways we have barely begun to imagine. The mysteries of Europa are not 22 puzzles waiting to be solved and forgotten. They are 22 doors, each one opening onto a corridor that leads deeper into the question of what the universe is and what we are in it. Behind some of those doors, we will find familiar things in unfamiliar places. Chemistry we recognize, processes we understand, conditions we can model and predict. Behind others, we will find things that have no place in our current understanding, things that require us to build new frameworks and new languages to describe them. And behind at least one of those doors, we hope, we dare to hope, we work and sacrifice and plan and dream that behind at least one of those doors, we will find something that looks back at us in whatever way it can and says, in whatever language chemistry and biology and time have given it, I am here too. We are not done wondering about Europa. We have barely begun. The ice is thick, the ocean is deep, the questions are vast, and we are small. But we are curious, and we are persistent, and we are, as a species, capable of extraordinary things when we are motivated by the right question. And the question of whether we are alone in the universe, whether life is a cosmic accident or a cosmic certainty, whether the dark and frozen ocean of a tiny moon in the outer solar system is empty or teeming, this is, without doubt, the right question. So let the spacecraft fly. Let the instruments measure. Let the scientists analyze. Let the questions multiply and deepen and branch into new mysteries we haven't yet thought to ask. Let the ocean keep its secrets for a little while longer, because the best stories, the ones that change you, the ones that stay with you, the ones that rearrange something essential in how you understand the world, are the ones where the answer, when it finally comes, was worth every moment of the waiting. And when the answer comes, if the answer comes in our lifetime, if we are the generation that discovers the first evidence of life beyond Earth, or if we are instead the generation that prepares the ground for those who will make that discovery after us, we should greet it with the same combination of humility and courage that every generation of explorers has had to find when they stood at the edge of the unknown and decided to take the next step. Jupiter rises above Europa's frozen horizon, enormous and banded and indifferent, its swirling storms larger than planets, its gravity reshaping everything around it. Beneath the ice, the ocean moves, slowly, constantly, driven by forces that have nothing to do with the small species now watching from so far away. The lineae crack and reform. The chaos terrain churns and refreezes. The hydrothermal vents exhale their mineral breath into the deep water. And somewhere in all of that, in the chemistry and the heat and the pressure and the time, something may be listening to the acoustic music of its world, tasting the chemical gradients in its water, moving through its dark and ancient home in ways that have no name in any human language, alive in a way that predates our curiosity, that has nothing to do with our existence, and that is, nevertheless, the answer to the oldest question we have ever asked. Are we alone? Not yet answered, not yet known, but asked more rigorously and more passionately than ever before, and pointed, with instruments and spacecraft and the accumulated intelligence of our species, at a small, cracked, ice-covered world that circles a gas giant in the outer reaches of a solar system in one of 100 billion galaxies in a universe that may be, for all we know, inexpressibly, unimaginably, overwhelmingly alive. That is what Europa is. That is what it means. And that is why, when the spacecraft arrives and the data comes in and the scientists lean forward in their chairs with their coffee going cold on the desk beside them, the world should lean forward with them. Because what happens next, in that data stream from 4 miles beneath the ice of a Jovian moon, may be the most important thing that has ever happened in the history of the human mind. The ice is 4 miles thick. The ocean is 60 miles deep. The question is 1 billion years old. And we are just beginning to ask it properly. What happens in Europa's ocean stays in Europa's ocean, unless we go and find out. And we are going. We are already on our way. Close your eyes one more time. Picture the ocean. Picture the dark. Picture the long, slow chemistry of a world that has never known sunlight, running its experiments in silence and in patience, driven by the heartbeat of a giant planet's gravity. Picture the possibility, real, measurable, scientifically grounded, and yet still dizzyingly uncertain, that in that dark and patient water, something lives. Now open your eyes. Look up. Jupiter is out there, beyond the orbit of Mars, beyond the asteroid belt, past the frost line, enormous and golden and surrounded by its family of moons. Europa is there, a tiny point of light near the king of planets, its surface gleaming with reflected sunlight, its ocean hidden beneath miles of ancient ice. We cannot see it with the naked eye. We cannot touch it. We cannot know it. Not yet. But we know it is there. We know the ocean is real. We know the question is real. And we know, because this is what the human species does, this is what has always set us apart, this is our great and terrible and wonderful gift, that we will not stop asking until we have the answer. The story of Europa is still being written. The most important chapters have not yet been finished. And Whoever you are, wherever you are, whatever time it is when you hear these words, you are part of that story. You are the generation that lives in the time when the question of life on Europa is open, when the answer is possible, when the spacecraft is flying and the instruments are measuring and the scientists are hoping. You are the generation that gets to wonder. And wondering, genuinely, deeply, rigorously wondering, is the beginning of everything. Don't stop wondering. Don't stop asking. Don't let the answer wait forever for lack of someone who cares enough to reach for it. Europa is waiting. And somewhere beneath 4 miles of ice, in an ocean older than the dinosaurs and deeper than anything on Earth, the universe may be holding its breath, waiting to be discovered. The question is out there. It always has been.
It is, are we alone?
And the answer, whatever it is in the dark, in the water, in the ancient and patient chemistry of a world we are only now beginning to know. The journey has begun. The story is not over. And wherever it leads, it will be worth every moment of the asking.